Now, in this particular question, I am going to explain to you all the need of a reference atom for measuring the atomic mass, and we are going to give you some information about the two reference atoms which are normally used in day-to-day life for chemistry. Now, onto the screen over here, I have the symbolic representation of an atom. We have a total of 3 subatomic particles: the neutron, the proton, and the electron. But before I give you the first point, understand that the neutron and the proton are the only 2 subatomic particles which have a considerable amount of mass. As far as the electron is considered, an electron is going to have negligible mass, which means the mass of an electron is so small that it's perfectly fine even if you don't consider it. Let's have a look. Let's write down. So the mass of an atom is obviously concentrated in its nucleus, and it is due to the protons and the neutrons which are present within the nucleus. Since an atom is very tiny, it was not possible to measure the atomic mass accurately. Obviously, the standard units that we use in day-to-day life for measuring regular masses such as grams and kilograms are too huge. The mass of an atom cannot be calculated using these particular units, and therefore to compare the mass we are going to use atoms itself as a relative standard of measurement unit. So who is the atom that we are going to select over here? The first one is going to be hydrogen and the second one is going to be carbon. Let's have a look. Therefore, the concept of relative mass of an atom was formed. Let me go forward with the first atom over here in consideration, which is going to be hydrogen, and let me explain it to you in detail. Now, to explain relative mass of an atom, the reference atom which is considered is going to be hydrogen. We have a definite number of atoms over here. So we have hydrogen, nitrogen, oxygen, sodium, aluminium, phosphorus, potassium. The basic thing that you will be able to see over here is that the hydrogen atom is the smallest. Its mass is very close to 1 Dalton. So in that particular case, every other atom should be compared to the smallest atom possible, which is hydrogen. Now how am I going to do that? Let me consider an atom of nitrogen. If I have a single atom of nitrogen, it is going to be 14 times heavier as compared to the mass of hydrogen, which means if I take 14 atoms of hydrogen together, I am going to get the mass of 1 atom of nitrogen. To technically represent it, let's have a spring balance, and in this particular case to the left pan we have a single atom of nitrogen and we have 14 atoms of hydrogen to the right. Both of these are going to exactly balance out each other. So let's write this particular information down, which is with respect to our first atom. Over here, the two reference atoms were as follows, and we have already explained to you the first one, which is the hydrogen atom. The hydrogen atom is considered to be the lightest atom possible. Therefore, the relative mass of hydrogen atom is considered to be exactly 1, and it is due to the 1 proton which is present into the nucleus. Remember, the electron does not have any mass. It is negligible in mass, so it's something that we don't need to consider. On the scale, the relative atomic mass of many elements was found to be fractional. So the issue is, as far as a single atom of hydrogen is considered, the mass is not exactly 1. The mass is 1 point something after the decimal point. So most of the atoms, the masses are going to come out fractional. So I need my standard of unit of measurement to be exactly 1.000. How am I going to do that? Let's have a look. I'm going to change my atom of consideration. Therefore, we are going to take the carbon atom as the reference atom. There's a slight issue over here. If I show you the carbon atom, the mass of a carbon atom is exactly 12.000. But I need my mass of ratio to be 1. So what am I going to do? I'm going to take that particular carbon atom, divide it into a total of 12 parts, and when I divide it into a total of 12 parts, I am going to get over here as 1/12 the mass of a carbon atom. Now think about this carefully. If I take 12.000, cut it into 12 pieces, and I take a single piece out of it, my mass that I'm going to get now is going to be 1.000, which is exactly what I needed, and that's better than hydrogen. Why do I say so? Because the mass of hydrogen, let's assume, is 1.008. So all of the other masses are going to come in fractional, but the mass of 1/12 to the mass of a carbon atom is going to be 1.000, exactly what I need. So let's write that particular piece of information down. Over here, who do we have to the left? We have an atom of sodium. Now, sodium atom is 23 times heavier as compared to 1/12 the mass of a carbon atom. So I will need 23 pieces of 1/12 the mass of a carbon atom to give me 1 atom of sodium, so that the pan is perfectly balanced. When we write this information down, let's have a look. So carbon atom is the second point. The carbon atom has now been selected as the reference atom. In this scale, the relative mass of a carbon atom is obviously accepted as 12. Not only 12, 12.000. After that, the relative atomic mass of one hydrogen atom is compared to that of a carbon atom. I'm going to take that carbon atom, divide it into 12 parts. When I do that, it becomes 12 divided by 12, which is obviously going to be exactly 1. And not only 1, it is going to be 1.000, the number that I need, the number that I require.